This is part 2 of the robot arm build. If you did not watch part 1, I recommend watching that first, because there I go through what I used, like the motors, the specs, the first joint design, and a lot of the small details behind the build. In this part we are building the full arm. I print the rest of the parts, assemble everything, wire all the motors, write some code, and start testing. And at the end I try something that I think is really interesting, but I will leave that for later in the video. Quick recap from part 1. I designed the arm in Fusion 360 to be modular. The idea is that I have one main link design that I can print more than once. So if I want more joints or a longer arm later, I do not have to redesign everything from zero. Now printing everything for the full arm. Now that the first joint works, I can move on to the real build. I print all the parts for the arm, remove the support material, and clean up the edges so everything fits properly. For the wires going to the ESP32, I use DuPont connectors. That makes it easy to plug the servo signal wires and the potentiometer feedback wires into the GPIO pins and move them around later if I need to. For the motor power, I solder the power wires together, then cover the connections with heat shrink to protect them and keep everything clean. To make the arm stable, I used the 4 M4 screw holes I designed into the base. Then I attached the base to 2 T-slot aluminum rails using fasteners. After that, I clamped the T-slot rails directly to my desk with 2 clamps. This makes the whole arm much more secure. Now the base is not sliding around, the arm is not falling over, and I can start testing without worrying that the whole thing will move every time the servo turns. It is a simple setup, but for testing, it works really well. Now I write a small program to move each joint and record the maximum usable movement of each motor. I want to know the real limits of the arm, not just what the servo is supposed to do on paper. Then I tape a sheet of paper to the desk and tape a Sharpie to the end of the arm. The goal here is not to draw anything clean yet. I'm just trying to find the edges of the robot's workspace, the area where the pen can actually reach. Then I tape a sheet of paper to the desk and tape a Sharpie to the end of the arm. The goal here is not to draw anything clean yet. I'm just trying to find the edges of the robot's workspace, the area where the pen can actually reach. After mapping the rough drawing area, I noticed another mechanical problem. The base and the vertical shaft of the arm were not as stable as I wanted. When the arm reaches out, it puts side load on the main column, and because that column is only supported at the bottom, it can move a little. That may look small, but on a robot arm, small movement at the base becomes a big error at the end of the arm. For the next version, I want to fix this properly with bearings and preload, so the shaft is supported much more like a real machine axis. But for this prototype, I went back into Fusion 360 and designed a quick support bracket. The idea is simple. The support screws to the base and wraps around the vertical column, so the column has extra support higher up instead of only being held from the bottom. It is not a perfect bearing system, but it works like a guide. It helps reduce the wobble and keeps the main shaft more stable while the arm is moving. After printing the support, the fit was too tight, so I had to sand it a little until the column could move freely. Then I added some grease, so the arm could rotate without rubbing too much or getting stuck. This is not the final solution, but it makes the prototype more stable and gives me a better idea of what I need to change in the next design. Taping the Sharpie to the arm was good enough for the first rough test. It let me quickly see where the arm could reach and how the workspace looked on paper. But for actual drawing, tape is not enough. The biggest problem is not just holding the pen. The real problem is keeping the tip of the pen in contact with the paper while the arm is moving. So I went back into Fusion 360 and designed a simple pen holder. It is made from small brackets that screw onto the arm and hold the Sharpie in a controlled position. This is still just a test design. It is not the final precision pen mechanism, but it is much better than tape because now I can actually adjust the pen contact instead of just guessing. After printing the parts, I assembled everything on the arm, tightened it down, and tested it. And for a first try, it worked really well. The pen holder gave me a much better way to control how the pen touches the paper, which is exactly what I need before trying more complex drawing movements. After the arm was built and the pen holder was working, the rest of this video became testing, adjusting, and testing again. I do not want to make it look like this worked perfectly on the first try. It did not. I had to keep changing small things, moving the arm, checking the result, adjusting the code, and trying again until I finally got something meaningful. At first the arm was mostly just scribbling, but even that was useful because every bad movement showed me something. Where the arm was too loose, where the pen was not touching correctly, and where the code was not matching the real movement. The last program I made for this version was probably the most useful one. Instead of only commanding the arm from code, I made a simple record and playback system. I can move the arm through a motion while the program records the joint positions, and then the arm can replay that same movement. It is still rough, but this was a big step. Now the arm is not just moving randomly or following fixed commands. It can record a real motion and try to repeat it. And that is a good place to stop for this video. This first version taught me a lot. The arm moves, the joints work, the pen holder works, and the electronics are doing what I need for testing. But I can also see the next problems clearly. In the next part of this series, I want to add a proper rotation sensor so I can track the real angle of the joint instead of only trusting the servo command or the internal potentiometer. That should give me much better feedback, and it will be the start of a more proper closed-loop control system. I also want to test better motors, improve the shaft design, and maybe replace the 3D printed shaft with an aluminum one. This version was the learning arm. The next step is to make it more accurate, more rigid, and much closer to the kind of robotic arm I actually want to build. Thanks for watching. Don't forget to subscribe, and if you have any questions, suggestions, or just want to say hi, don't hesitate to leave a comment.